All right, let's jump right in. Today, we're going to tackle one of the coolest, most powerful tools in all of math and physics. But don't worry, this isn't going to be some dry, dusty lecture. Instead, I want you to think of this as a detective story. We've got a really complex case on our hands, and we're about to meet the specialist detective who knows exactly how to crack it wide open. Okay, so here it is. This is our central mystery, the forced one-dimensional wave equation. So what does this even mean? Well, just picture a guitar string, and imagine something is continuously shaking it, some external force that we're calling f of x comma t. The big question, the case we have to crack is this. If we know exactly what that shaking force is, can we figure out the precise shape of the string, u of x comma t, at any given moment in time?
So here's our game plan for the investigation. First, we'll set the scene. Then, we'll introduce our specialist detective, the Green's function. After that, we'll lay out the master plan, the interrogation, if you will. We'll see how we can isolate the solution and then finally unmask our detective before we close the case with this beautiful, powerful idea called superposition. Let's get to it.
All right, first things first. Every good detective needs to properly survey the scene of the crime. For us, that means we need to understand all the rules, all the conditions that are governing our vibrating string. So here's our official case file. First up, we have the law. This is the wave equation itself, the fundamental physics of how the string moves. Second, the boundaries. This is crucial. Our string is tied down, fixed at both ends. Let's say at x equals 0 and x equals L. So the movement, the displacement there, has to be 0, always. And finally, the starting point. We're going to say that the string starts out perfectly still and perfectly flat. Getting all these details right is the only way we're going to find the one unique solution. Okay, with the case file laid out, it's time to call in the expert. This is a tough case, you know? We can't just brute force it. We need a very specific, very clever tool. We need our specialist detective, the Green's function. But before we can really meet our detective, we have to understand their favorite type of clue. It's called the delta function. So forget that complicated, continuous force for just a minute. What if, instead, we just gave the string one single, sharp tap? An instantaneous little poke at one specific point in space, let's call it xi, at one specific moment in time, tau. That's what a delta function is. It's the simplest, cleanest, most fundamental clue you could possibly imagine. And this is exactly where our detective comes in. The Green's function, which we call g, is literally defined as the system's reaction to that one simple clue. It's the answer to a very specific question. If I poke the string right here at this one spot xi, and right now at this one time tau, what's the ripple going to look like over there at point x, a little bit later at time t? It's the system's fundamental fingerprint, its impulse response.
Now this is where it all starts to click. Just look at the beautiful parallel here. On the left, you've got our big, hairy, difficult problem. Some wave operator, L, acting on our mystery solution, U, gives us some complicated force, F. But on the right, that's the detective specialty. The exact same operator, L, acting on the Green's function, G, gives us the simplest thing possible, that single tap, the delta function. And the whole strategy, the absolute genius here, is realizing that if we can just solve the simple case, we can use it to build a solution for the complex one.
So what is the detective's strategy exactly? How do we leverage that simple case to solve the hard one? Well, it involves a really clever, four-step mathematical interrogation.
Here's the plan of attack. Now, I know it looks a bit abstract, but trust me, every step here is deliberate. We're going to take our two equations, multiply each one by the other's solution, subtract them, do a clever rewrite, and then integrate the whole shebang. This whole process is designed to back our suspect, u x comma t, into a corner where it has no choice but to confess.
And now, the moment we've been waiting for, the payoff. This is the part of the story where the detective's seemingly crazy plan works perfectly. All the clues just snap into place, and the solution reveals itself. Okay, so after we do the first two steps, multiply and subtract, we land on this expression. Now at first glance, yeah, it looks more complicated, right? But believe me, this specific combination of terms is no accident. This structure is perfectly engineered to do something amazing in the very next step. And here is the magic trick. That whole messy-looking thing from the last slide, it collapses, it rewrites itself perfectly into a neat collection of total derivatives, or divergences. This is the mathematical equivalent of the detective taking a table full of chaotic evidence and neatly organizing it into labeled folders. Why? Because expressions that look like this are an absolute dream to integrate. We're setting ourselves up for the final step.
So when we do that final integration step, the fundamental theorem of calculus tells us we're going to be left with a bunch of terms evaluated at the boundaries, the edges of our space and time. But here's the kicker, and this is the best part. They all go to zero. They just disappear. The time boundary terms, gone, because the string started at rest. The spatial boundary terms, poof, gone, because we know the string is tied down at the ends. It's like all the false leads and red herrings in the case just evaporate, leaving only the truth behind.
And after all those boundary terms vanish, this is what we're left with, the confession. That integral with the u and the delta function on the right side of the equation, its whole job is to simply pick out the value of u at our specific point, xt. And there it is. We've isolated our solution. U of xt is equal to this big integral, which involves the force f we started with, and our detective, the Green's function g. We finally know how to find the answer.
This is awesome. We have a formula for the solution, but it depends on g. We know what g does, but we still don't know what it is. It's time to unmask our detective and find the explicit formula for the Green's function itself.
So let's just ask the question straight up. We know it's the ripple from a single tap on the string, but what does that ripple actually look like mathematically?
Well, the key here is to speak the problem's natural language. And for a string that's pinned down at 2 points, that language is sine waves. I mean, it just makes sense, right? Sine waves naturally hit 0 at regular intervals, which is a perfect match for our condition that the string is tied down at x equals 0 and x equals L. They are the fundamental shapes, the natural modes of vibration for this entire system.
So here's the strategy, laid out nice and clear. We take our unknown Green's function, g, and we express it as a sum of sine waves. Then, and this is the really clever move, we do the exact same thing for our simple tap, the delta function. We express it in the language of sine waves too. Once everything is speaking the same language, we just plug them back into the main equation, Lg equals delta, and we can match up the coefficients for each individual sine wave. And just like that, one incredibly difficult partial differential equation transforms into a whole series of simple, ordinary differential equations, which are way easier to solve. It's just an elegant way to break the problem down.
So, we've found our solution formula, and we've constructed our Green's function. The case is officially closed. But what's the big, underlying physical idea that made this whole thing possible in the first place? You know, this quote from the source material just says it all. That big integral formula we found, it's not just a mathematical trick. It embodies a really deep physical principle: superposition. You can think of that complex, continuous force F as just an infinite number of tiny, infinitesimal delta function taps happening all over the string all the time. The Green's function gives us the response to each one of those individual taps, and the integral, that's just us adding up or superposing all the responses from all those taps over all of space and all of time to get the total final vibration. It's beautiful.
And that leaves us with one last thought. This whole detective story, it wasn't really just about a vibrating string. It was about a universal way to solve problems. It's this idea of breaking down a complicated, messy problem into its simplest, most fundamental components, solving for those little pieces, and then just adding them all back up to get your final answer. You see this powerful idea everywhere, from electromagnetism to quantum mechanics. So the question I want to leave you with is, where else in your world could this way of thinking apply? Thanks for coming along on this investigation.